Interesting. And thank you for the participants. Nice to see a lot of faces and like talk about homotopy theory and everybody can understand about things. So okay. So today I will want to give you the ideas behind Floer homotopy theory, and I will use the analog of Morse theory. And later on, I will say a few words about how you move between them, kind of, and what is the motivation. So we are going to study like the X be a closed smooth manifold. Okay, so I have the privilege to draw a lot of pictures on the board, and then you can believe me that there is a mathematics behind the pictures. So this is X, and we want to study a lot of like invariants from algebraic topology and give them a geometrical meaning. So how are we going to do that? We're going to take, and this is the real numbers, and we're going to take some nice function, and when I say nice, I mean like f is Morse. Morse is kind of non-degenerate and kind of like a compactness condition, and it's maybe some transfer side condition. And we'll see in a moment how these conditions take place. And we begin by okay, we define like crit P will be the so first will be the critical points of F of index P. So what is index? Index is the, like maybe say it like that, the dimension of the downward like subspace. So for example, the index, so this will be the index of critical points. So first we'll say that we have 4 critical points, like 2 maxima, 1 minimum, and 1 saddle point. Okay, so the minimum point, and maybe when I say downward, I say according to F. So the minimum point.
I think your F was a right word, not.
No, I mean F. Okay, in this specific case, F is the projection on the z-axis. Yeah, okay. Maybe if I want to be a little bit more precise, I can say that you can look at the Hessian of F, and the index is the number of the -1 if you like take the form of this Hessian to be like ones and -1s. But let's look at the picture, and so this point have index 0. This point have index 1 because we have only one direction which goes down, like according to the height function, and this maxima have index 2. Like in general,
so this is like a 2-dimensional manifold sits in.
Yeah. So this is this manifold is like a homotopic to S2. It's like the heart-shaped sphere.
Okay.
Yes, thank you for that question. Okay, and okay, yes, and now we try. Okay, so and the maybe one of the pioneers of this theory was like Morse, and these ideas go, I don't know, like Morse about 30, and the first thing maybe we can say that we can calculate the Euler characteristic of the manifold using only by knowing this number of critical points. So we have that we can write it like that. So this is maybe the basic and the first example to see that we took a invariant from algebraic topology and rewrite it as a like geometrical invariant. Okay, So the next thing that we want to try to do is to calculate. We want to try to calculate the homology of X. We'll do like the baby case of the homology with coefficient sigma 2. So I can easily describe you the chain complex that will calculate this thing. So the P part of the chain will be the Morse chain complex. So we will be sum of all critical points of index P, Z 2. And now I need to tell you what is the differential. So let's take two critical points. Also X, the critical point is index P minus 1, Y being critical point of index P. For example, let's take this point to be Y, and this point to be X. And we try to count downward gradient flow lines. So maybe I say more precisely, we want to look for like gamma, which are like half in our manifold, such that like gamma of infinity, kind of like the limit is X, and gamma of minus infinity is Y, and gamma is a gradient flow line, meaning that the derivative of gamma equals to minus F of gamma. Okay, so let's again, I will use my drawing skills. For example, in our situation, we have like one flow line, which is this one, which goes from Y to X. Maybe let's add another one, or we call this point Z. And in the example of X and Z, we have like two flow lines, one going like front, one to the back. And we denote by M Y X the set of flow lines. And this is a flow line from X Y to X, flow lines from Y to X. And the differential, like the coefficients of the differential, will be exactly counting mod 2, the size of this set. And maybe I will say that the fact that the F is Morse gives that these sets are finite. So the differential D Morse of this point Y equals to the sum over all the x's is like the right index. And when we take the size of this manifold, it may be mod 2 times x.
Okay. What is phi again? It's the
Phi is the index, critical point of index. So index P is a natural number, which like again goes from 0 to the dimension of the manifold.
So in your example, there's two of index 2 and one of index.
And one of index 0. Yes, exactly.
Is the significance of working mod P that you don't have to frame these amps? Is the significance of working mod 2 that you don't need to worry about
Yes.
framing amps?
Yeah. Okay, I don't want to tell you about framing, so
Don't tell.
yes. Maybe later I will say if you want. Okay. So the first example was calculate this variance, and the okay, so maybe I will say that indeed, like a theorem, yes, that okay, it's not clear exactly, but this idea goes back to Milnor. Mail from about something like that, and that indeed the homology we are getting for this Morse complex of X is like the singular homology or a cellular homology or whatever you want of X. If you want, you can also have like a quasi-isomorphism between the chains, but we don't go into these details. And our next, okay. So our next goal is to again to generalize this result. So what I want to generalize, that's a good question. So as Lior told us, we have a homology theory. Okay, I'm not sure if he exactly say that, but we have at least graded rings, like graded ring, which we denote by that. We'll remember. We say that this is the like ring, graded ring of n-dimensional low manifolds up to this relation that we will draw like that. Up to bodies. And okay, and as we Lior said, we have that this the zero-dimensional group is ZIMO2, like generated by a point, and like if you have even dimension of point, you can take a line between them, which will be a Bordism. And in this talk, I want to generalize the coefficients in ZIMO2 to be the coefficients of kind of this ring, and by that I mean that we have a spectrum. So denote by MO such that the homotopy groups of MO are given by this graded group. So our goal is to generalize this result to the following result that I want to target like that. Maybe more generalized, but less pretty. We want to calculate this generalized homology of the manifold using the geometrical data. So the first thing is I want to generalize the method of calculation. So we replace chain complex, the chain complex as the calculating tool by spectral sequence. So instead of having like this chain complex, we will take like the first page will be the direct sum of critical points index P over this ring, and by that I mean that we have the first page as place N and P will be this thing. So for example, for this sphere, let's draw it. We have like Z mod. We have like Z mod 2 on the diagonal, which represents like that we have one critical point of index 0, one critical point of index 1, and two critical points of index 2. Like this is the P axis, and this is the N axis. And like here we have, what is the second one? It's 0. And so on, like all the higher Bordism groups. And now I need to tell you like two things. What is the rth page and what is the differential? So the first differential, the first page will be exactly this thing that we just defined, like the flow manifolds of consecutive indices.
So what is it by grading here? P is clear.
Yeah,
And
so-
omega n. And
Thank you very much. So, and so indeed, like these, the first differential is still given by this like a multiplicator. Maybe I'll write more carefully. It's like if you have an element here, maybe so this is you have one manifold for each critical point. So let's take a manifold here n. So the differential of n is given by by Cartesian product of like x y x. I mean, if we have like n, which was that came from a critical point of index p, which is in this case y. Let's call them y to be more consistent. So I just want to say that this is the same as the differential in the chain complex as usual. But to talk about the higher differentials, we need to introduce some new ideas. So, okay, maybe first I will draw you a picture. And just maybe intuition for what I'm trying to do. So in the next page, the differentials, I mean, maybe we have here like some z mod 2 and some, okay, maybe here we have some specific group. And here then we have like z mod 2, and here we have z mod 2. And the differential in the second page needs to be maps like that. So I somehow need to specify you a map that take, for example, for this differential element in this graded ring, in this group, sorry, and give you such a group, I need to take 0-dimensional manifold and give you 1-dimensional manifold. So how are we going to do that? So first, let's draw maybe more abstract picture. So for now on, for simplicity, let's assume that we have only one critical point of each index. So let's imagine this is the critical points of index p, p plus 1, p1 minus 1, p minus 2 maybe. And you can maybe see in this picture, or just believe me, that in general, the moduli space of flow manifolds between, like, for example, two critical points which are not consecutive, maybe it's the general case, this space is not closed manifold, it's not even like a compact manifold, and the boundary of flowing from, for example, p plus 1 to p minus 1 is given by what we call the broken flow lines. So maybe, so I have like a lot of ways to flow to this point, and like the boundary is given by flowing first to this point and then to this point. Maybe in this picture it will be more clear what do we mean. So the moduli space of flowing from y to z is given by, like, I draw the representatives, which is, sorry, this open interval. Each point here represents the flow line that coming from y to z through this point. Yeah, for example, we have all these flow lines. We have this open interval family, and the boundary is given by the broken flow lines, which in this case is flowing from y to x and from x to z. And indeed, we have that the boundary of the open interval is 2 points, which corresponds to flowing from y to x and from x to z in these two different points. Great. So let's write the general phenomena. So in general, we have that the boundary of the compactification of the modular space of flow lines is given by this union of like let's call them, I don't know, X, which is the critical between P and Q. Let's write it like that, like less than yes. Yeah, my interval is maybe the opposite. So I take critical points with index strictly between Q and P, and I take the Cartesian product of the manifold, which is like flowing from Q to X and from X to P. Yeah, and if I, for example, in the case that the difference of the indices is only 2, I get that this manifold is only boundary, but if the difference of the indices is like more than that, we get a corner structure. For example, this will be the codimension 1 strata, and the codimension 2 strata will be maybe to factor our broken flow lines. For example, we can do flow from here to here, but we can like broke it to more than 1 point. Yeah, like that. So in this case, the codimension 2 strata will be like that. And in general, every Morse function on the manifold give us this, let's call it a coherent chain complex of manifolds. Draw that. We'll see what I mean. So we have, like, for example, indeed, these points are the critical points, and I use the assumption. So I have exactly 1 critical point in each index. And so we have the 0-dimensional moduli spaces, which you can think of them as like the differentials, as we saw. But we have that the like the 1-dimensional flow lines has the boundary, which is the multiplication for these 2 manifolds, and like so on. This manifold is like 3 minus 2, and the boundary is the multiplication, and like we have even higher moduli spaces, and for example, in this case, the boundary of the manifold from P to P minus 3 is given by the union of like this multiplication. I mean, it's not concatenation, it's multiplication, and this one. In this structure, like this coherent structure of manifolds with corners, we call this thing like a flow category. And now we can try to say or try to give intuition about the higher differentials. So,
Wait, what is the flow category?
a flow category is a thing that looks like that. I mean,
Like, you gave me a kind of object. What is it in a categorical language? It's an object of a flow category. It is a flow category.
no, it is a flow category. A flow category is a bunch of points with some maybe indexing function,
Okay.
and a bunch of manifolds, a coherent family of manifolds. Yes.
What is coherent?
I mean that the boundary of the 1-dimensional manifolds is the product of the 0-dimensional manifolds, and like this structure, this corner structure, and like. So first, let's take a look at the like elements in the second page.
So
So,
like every, in the structure of a flow category,
yes,
every object has a number that corresponds to like an index? Or is it like, yes? And then if I want to map between points of different indexes, I need to provide like, okay.
it's like the mapping space between two objects is a manifold with corners, with like
Of
the
dimension?
dimension, yes,
Which is the difference between the indices, right?
-1.
-1. Okay,
And this is what you need to define a complex in some infinity category as a function from this.
Yes. Yes. Maybe I say a few words about it later. Yes. But it's a great perspective. So for example, let's draw, for example, okay, I promised you like assumptions, so let's take exactly thing with one object for each index. And for example, if this, so we have, I say that, for example, you can take n to be like this is n equals 2 and p equals 2. So we have element n which live in like 2 minus 2, which is like a 0-dimensional manifold. And if n survive, so maybe let's say first like that, n survive to the second page if you have a flow category with n over here. Here is the point of index, like maybe 2 in this example, and here you take the like the subcategory of the category that correspond to the Morse function. So in this example, I write here like m to 1 and n survive like in the kernel of the first differential to E2, if and only if you have a flow category like here with n here, and all this like part is like maybe I'm not sure how to write, but this is the restriction of the flow category coming from F. So in this specific example, you just need to give me a manifold like that. Like let's call it, I don't know, let's call this element X. So you need to provide me one more manifold, nx1, which like give you evidence to the fact that n survived to the second page, which is in the geometrical perspective a null Bordism of this multiplication, which is indeed like the first differential of n. So yeah, so like this is the specific case that if we can extend in union like I don't know, the restriction of the flow category of F to the indices like P and P minus 1. And okay, maybe I'll write the general thing after that. And to describe you the second differential, so the 2 of n is given by this construction. So if n survives to the second page, you can draw this thing. And we have the flow category that came from F. So we can draw also the flow category. And we have here a one-dimensional manifold. And we have here a one-dimensional manifold. And we can take, we can glue them together. And by gluing it, I mean that the manifold nx1 times m10 and the manifold n times m21 have like the same boundary, which is given by the multiplication of all three zero-dimensional manifold in this case. And we can take the colimit of this diagram. The colimit of this diagram, which is like gluing this to one-dimensional manifold along the boundary, is the second differential. So like if we try to give you the like a general statement, let's try to find it. In general, we have that. Theorem up to the fact that I didn't define half of the things precisely. So there is, let's, it's the like flow, and there is a Morse function, Morse main function. And that is the spectral sequence, and with like the first page is given like that. Minus p, and an element like n in some group like that survive in E r plus 1 if and only if you can extend it. You can extend the following diagram, which begin with n and continue up to p minus r, where here I put all like the higher manifolds aim from f. Here I put n, and I mean you just need to give me like the all these small manifolds and also the big one, and like the r plus 1 differential of such n that survive is given by extend this diagram one more step to p minus r minus 1, like that, and gluing all these manifolds, and we get like a closed manifold. I mean, I don't give, of course, I don't give you all the details, but I mean, you can like mimic this procedure. In general, you have a punctured cube diagram, and like here you have the 0-dimensional manifolds, or maybe the dimension of n manifolds. Here you have like all the manifolds that came from different ways to multiply manifolds from here to here, and you can glue them together, and this thing have a structure of a manifold. So at the end, we get an element in the right. I'm not sure exactly what indices we need. I think it's something like maybe that. I'm not sure. I will think about it in a moment. How much time we have? Minus 4 minutes?
Yes.
Thank you. Okay, so maybe I will say like 2 more words. First, I mean, maybe one want to ask, we can generalize all this Bordism structure to be stable frame Bordism. I mean, it's a fact that these moduli spaces of flow manifolds have a framing, like specific framing that comes from F. So you can take framing everywhere. And if you take framing everywhere, I mean, like in general, I promised you to calculate this thing. So the framed version is like ER in the framed version converge to like the stable homotopy groups of the manifold. This is maybe one thing to say. The other thing is that, okay, so this method of calculating stable homotopy groups, it's far from being effective. I mean, it's really hard to calculate the, maybe it's not so hard to calculate the flow manifolds, but it's really hard to understand the framing and glue them together and understand what framing you get. But sometimes, and by sometimes I mean like in Floer homotopy theory or in Floer theory, you don't have an underlying object like underlying topological object like X, and you just have this structure of flow category. So like, give me a second. So you can't do the procedure of taking some I don't know, topological thing and get a flow category and maybe calculate its pi star or some other invariant. But you start with a flow category, like you start with a geometrical data which is not like manifold, it's like, I don't know, maybe some strange moduli spaces that give you flow category, and you now can extract the like homotopical invariant directly from the flow category. So maybe it's the important perspective from flow homotopic category on all this stuff.